As the title says, today I will talk about some topological aspects of random graphs. To set what I'm going to do, so throughout the talk, the following questions form the central theme or the guiding theme. The first question concerns the typical genus of Edo-Shreni random graph. So in other words, is Edo-Shreni random graph planar or not? Or it does have a genus, given genus G. Of course, it depends on the edge density, as you might imagine. Second question is how a topological constraint, such as being planar or imposing an upper bound of the genus, influence the component structure of random graph, such as how the order of the largest component, or even the second largest component is different from the Edo-Shreni random graph case, and so on. The third question is the length of the longest and shortest cycles. In the Edo-Shreni random graph, the classical result, and in a random planar graph, let's say to make the life easy, I will just focus on the random planar graph later. So these are the kind of guiding questions throughout the talk. To give you some context, what am I going to do? Or let me briefly discuss some classical results on the Edo-Shreni random graph that are relevant to these topics or these questions. Of course, those who in the audience, I can imagine that there are quite many people who know very well about classical Edo-Shreni random graphs. So you can skip the first 7 to 10 minutes if you wish, because I will just wrap up what we know as a benchmarking results that we are aiming for toward the random graphs on surfaces. To set the scene, let curly GNM, so curly GNM, denote the class of all vertex labeled simple graphs on the vertex set of integers 1 through n with m edges. Typically m depends on n. And GNM be a graph chosen uniformly random from that class. And this GNM with our calligraphic symbol is also known as the Edo-Shreni random graph or the uniform random graph. There are many names. Throughout the talk, we often study the properties that hold with a probability tending to 1 as n tends to infinity. We just say it with high probability and WHP in short. And all the asymptotics throughout this talk are taken as n tends to infinity. Yeah? So many parameters will depend on n, and n tends to infinity. Yeah, this is the setting. As you might have known, one of the most striking results about Edo-Shreni random graph is the so-called emergence of the giant component. To be more precise, let L1 denote the largest component in Edo-Shreni random graph GNM, and we are interested in the number of vertices in L1. Of course, one can also talk about the number of edges, number of triangles, and so on, but we will focus on the number of vertices in this talk. And what Edo-Shreni discovered is that the order of the largest component, or the number of vertices in the largest component, I will just call it order, changes drastically when the average degree d passes through 1. To be more precise, let me parameterize the number of edges m to be d times n over 2 for a constant d. Yeah, so d is just the average degree. What we know is that if the average degree d is smaller than 1, then with high probability, the order of the largest component is a most log n. So illustrated with the small bubbles in the picture. On the other hand, if the average degree is larger than 1, then there is a component of linear order, while the other components are of small order, much smaller order, indeed, of log n. Therefore, we call such a largest component also the giant component. As I illustrated here, the big giant and the rest. And some of you might capture how I draw this picture. Indeed, the right-hand side picture, I have just copied of the picture on the left-hand side and scale it down. Indeed, this is known as the symmetry rule of the Erdős-Rényi random graph. Namely, if you delete the giant component from the graph, the so-called fragment behaves like in the subcritical Erdős-Rényi random graph. Yeah, this is the well-known symmetry rule. Let me see what is the name. Furthermore, if the average degree is larger than 1, so I just say that the order of the largest component is linear, but we can say even more. And also it explains why the average degree d is equal to 1 is so crucial here. Namely, via the coupling with the Galton-Wasson tree. So the same setting, so m is d times n over 2, when the average degree d is larger than 1. Now let rho be the unique positive solution of the transcendental equation. 1 minus rho is equal to exp of the minus d times rho. If you came from, say, classical probability theory, you will recognize that rho is indeed equal to the survival probability of the Galton-Wasson branching process with offspring distribution Poisson mean d. Yeah? Each individual has an independent Poisson distribution with mean d, and so on. And rho is indeed the so-called survival probability. And indeed, you can make such an heuristic rigorous so that we can say that the order of the largest component is indeed asymptotically rho times n, namely the fraction of the vertices that lie in the giant component is asymptotically equal to the survival probability of the associated Galton-Wasson tree or Galton-Wasson process, and this rho behaves like in this curve. Yeah, so it's a solution of the transcendental equation. That's a pretty nice result indeed by Kapp and other people, and this became a standard method nowadays, coupling with branching processes. Now, returning to our question on the genus of a Erdős-Rényi random graph, one of the very first results by Erdős-Rényi indeed concerns the planarity of the Erdős-Rényi random graph G and M. And surprisingly, maybe not surprisingly, the planarity also undergoes a phase transition when the average degree is around 1. So in particular, if V is smaller than 1, the average degree is smaller than 1, then one can show that with high probability, each connected component is either a tree or it contains one cycle we call unicyclic component. And therefore, it is embeddable on a sphere. So we call it planar. If a graph is embeddable on a sphere without crossing edges, then we call it planar. Yes, it's a planar with high probability because trees can be embedded on the sphere. Unicyclic components can also be embedded on a sphere. Collections of all of them can also be embedded on a sphere without crossing edges. Therefore, with high probability, the so-called subcritical Erdős-Rényi random graph is planar. On the other hand, when d is around 1, some complex components emerges in the sense that the largest component contains at least 2 cycles. Even more complex structure appears, namely, with a high probability, G and M will contain a subdivision of the complete bipartite graph K33. Yeah, so according to the Graf-Stiegler theorem, according to the Graf-Stiegler theorem, if a graph contains a topological minor or the subdivision of complete bipartite graph K33, then it is not planar. Yeah? Therefore, GNM is indeed not planar. It is not planar, but what can you say about the genus? Of course, it's not planar. It's genus 3 or million and so on. So this is what we are interested in. First of all, yeah, to determine the typical genus of GNM. And another question, another thing that this result leads to us is if we a priori restrict ourselves on the graphs that can be embedded on a sphere, what can we say about the component structure or the cycle structure? Can we say more? Global and local structure, indeed. What can we say about that? Therefore, in the second part of my talk, I will talk about this random planar graphs. Random planar graphs, let me first set the scene and then let me kind of mention some different objects that are studied commonly. So as before, the curly P and M will be the class of all simple graphs on vertex at n with m edges now that are embeddable on a sphere without crossing edges. And P and M will be a graph chosen uniformly random from P and M. So it's a uniform random planar graph. Note that I'm talking about the graphs that can be embedded on a sphere. In literature, there are so-called plane graphs or planar maps. Those are the graphs that are embedded on the sphere. So embedding is already taken into account, and those objects are often studied in statistical physics, also in Immersive Combinatorics community. A lot of the French community people are working in this direction, like from the probability theory point of view, the local limits, and so on and so on. So don't be confused with these two different notions. We are talking about the graphs that can be embedded. Simply, of course, the class of all planar graphs is a subset of the class of all graphs without any constraint, triviality. And due to the famous Euler's formula, we also know that there are no planar graphs with more than 3 times n minus 6 edges. 3 n minus 6 edges are achieved only by planar triangulations. Furthermore, thanks to the previous result, when the average degree is strictly smaller than 1, yeah? So when m is smaller than n over 2, in other words, the average degree is strictly smaller than 1, we know that GNM is with high probability PNM. In other words, in terms of the enumeration, the fraction of the planar graphs over the set of all graphs tends to 1. Yes, just plain rewording with the terminology with high probabilities. Do you have any questions? Please ask. Yeah, I do not see this chatting box, to be honest. So anytime you have a question, just ask me. This is a drawback of these online lectures. Yeah? So in the lecture hall, you just raise your hand. So you can ask anything. This was up so far as trivial, but nevertheless, it tells us that in order to talk anything sensible or interesting properties of a random planar graph, we are enough to focus on the case when m is between n over 2 and 3n. In other words, when the average degree is between 1 and 6, right? N over 2m, yeah, right? 2m over n is the average degree. Indeed, when I was very young, indeed, I spent 6 months in Poland, Poznan, and I learned a lot about the random graphs from the master, Tomasz Uchak, and we studied the giant component. And we focused on the range that I mentioned when the average degree is between 1 and 2. There are surprisingly 2 critical periods in the evolution of the random planar graph. The first one occurs when the giant component emerges, like in the Edosh random graph, when the average degree is around 1. Yeah, so 1 was the same value. And the second one occurs when the giant component contains almost all vertices. Almost all, of course, sometimes error term is little of n, sometimes error term can be also some other term. Yeah, it can be stronger result, but from our glass, we will just scale the size of the largest component by n. Therefore, this is the right window, right scaling that we are interested in. And this, surprisingly, there is the second critical period when the giant component contains nearly all vertices, and this happens when the average degree is around 2. And such a phenomenon was not observed previously in any sensible natural random graph models. Another surprise is that when the average degree is between 1 and 2, the fraction of the vertices lying in the giant component, so L1 divided by n, grows also linear in D minus 1, just linear, instead of the transcendental behavior that we have observed in Eder-Shreni random graph. It's more straight line. In comparison to the Eder-Shreni random graph curve will look like this. Huh? Yeah, there are many interesting things. So I don't know whether I'm talking about everything. Furthermore, so this is indeed an interesting slide. I'm saying a lot. Furthermore, I mentioned that in the one of the very first slide, I was mentioning what was the question? Could you ask it aloud? Because as I said, I do not see the chat box.
The question is if for planar graphs, it's K5 and K33 minor free.
Minor free, yeah,
Yeah,
Kratov's key
did
theorem.
you use this minor free property in the random planar graph proof?
Not here, but when we say that the Eder-Shreni random graph GNM is not planar when the average degree is larger than 1, then we prove that there are copies of topological minor of K33. I just say bypassing K33. K5, the minor of K5 appears much later because it's dense. If you look at it, the density, edge density of K33 and the edge density of the K5, you can imagine the K5 appears much later. Did I answer the question?
Yeah,
very good question. But when we talk about the random planar graph, of course, we are restricting ourselves on those graphs without containing K5 and K33 as minor. Yeah, we are looking only all those. Then it behaves like strangely enough. Yeah, what I mentioned earlier is that Eder-Shreni random graph, when average degree is larger than 1, there is this famous symmetry rule, namely when you delete the giant component from the graph, the leftover, we call it fragment. The fragment is a subcritical random graph. In contrast here, from the random planar graph, when the average degree is larger than 1, if I delete the largest component from the graph, the fragment is not subcritical, but it is critical. So there are many components fighting each other to become a leader. So quite different. It does not follow the symmetry rule as observed in the Eder-Shreni random graph GNM. Yeah, it's very interesting. Having such an interesting result, to be honest, a natural to some people, a natural question is what other classes of graphs undergo phase transitions like here, yeah, like random planar graphs. From a glance, from a very from a distance, if you look at the L1 divided by n, it looks like this graph, like blue and red graph. This black part is just copy and paste of the Eder-Shreni. Yeah? So the interesting part is the blue and red. What other classes of graph may behave like this? A natural candidate is, of course, class of graph that are embeddable on a sphere. This is a summary. I forgot. Yeah, I had this picture and then I forgot that I had this picture. This is this clear distinction that in GNM and in PNM. Yeah, so what are the classes of graph behaves like this? And the natural candidate for that is random graphs on surfaces that I will talk about later. Yeah. So now let's observe this graph a little bit more. When we study phase transitions and critical phenomenon, then the most interesting things and most difficult things happens around the criticality. So when average degree is around 1, yeah, not strictly smaller than 1, not strictly larger than 1, but when average degree tends to the critical value 1, tends to 1. But of course, when we say tends to 1, what is important thing is how fast it converges to 1, right? The speed. As it turned out that the right scaling turned out to be in this fashion, so-called weakly supercritical. It's not just supercritical, but tends to supercriticality. So when M is n over 2 plus S for a positive S, so positive meaning supercritical. When this is smaller than 0, then we call it weakly subcritical anyway. But more important thing is the S. S is much, much smaller than N. Therefore, M tends to N over 2. So average degree D is to M over N, yeah? Tends to 1 as we wished. But how fast it can converge to 1 is captured by this one. It can't be slower than n to the 2/3. It should be faster than n to the 2/3. Yeah. Then a very famous and influential result by Bolobash and Uchak says that the order of the giant component in the weakly supercritical regime is about 4 times S. Yeah, this S is the same S. 4 times S. Yeah, the giant component grows 4 times this surplus. M minus 1 over 2 is equal to S, right? S. On the other hand, in the planar graph, Uchak and I show that indeed the order of the giant component is 2 times S. Asymptotically 2 times S. Roughly half the order of the giant component or the largest component of the Erdős-Rényi random graph. So the planarity constraint imposed on the graph make the edges spread over maybe more evenly over different component. In comparison to the rather kind of a greedy fashion in case of Erdős-Rényi random graph, the richer get richer. If the giant component will observe more edges without any restriction over time. If you think of it as a kind of dynamics, although the analysis of dynamical model is more difficult, nevertheless you can imagine. Yeah. There is a penalty due to the planarity that not every edges can be inserted in the can be inserted within the largest component, but they are also inserted between and outside and so on and so on. There is a penalty that it becomes half the size of the giant component comparison to the Erdős-Rényi random case. Of course, if you think about it, the edges, they could not be inserted into the giant component, of course, also affects the outside of giant component, namely the fragment. I talked about the fragment. And the fragment in planar graph is, as I said, it's the critical, it's much, much larger. It's like n to the 2/3. Whereas in the Erdős-Rényi random case, the fragment is much, much smaller than n to the 2/3. While here, in the planar case, the fragment is even of order n to the 2/3, much, much larger and very complex. So there is this effect due to the planarity constraint. It's a lot of nice properties are going on. I just write it in this one line, but of course you can imagine that there are other interesting properties that I didn't write. Yeah, otherwise it will become too crowded. Are there any questions? Yes, it's a very interesting indeed phenomenon. If not, I just return to the topic that I was mentioning already earlier. If you look at such a behavior, in particular this linear, not this finer scaling, but the other, what other classes of graphs undergo such a phase transition? And I told you that, of course, natural thing is sphere, and then surface of constant genus, surface of increasing genus, and so on. So it's a natural to study random graphs on surfaces. To set the scene, we will just focus on the random graphs on orientable surface of given genus G. G will be any non-negative integer. Given G, you think of the orientable surface, I mean the sphere with the G handles, and we will consider the set of all class of all graphs embeddable on the sphere. In other words, a graph with genus n most G. Yeah? Planar graph can be embedded on a torus, so it's inclusive. Yeah? So SG will be the class of all graphs with the genus n most G. In other words, the graphs that are embeddable on an orientable surface of genus G. And S sub G and M will be a graph chosen uniformly at random from the class. And trivially, P and M, the class of planar graphs, is when the genus is 0, and this is included in the graphs with the genus n most to G. And of course, this is a subclass of all graphs without any constraints. When you look at such an inclusion, one of the natural question is for which genus G, depending on n, are two random graphs, G and M and SG and M, indistinguishable. But indistinguishable, but what? We are talking about the two probability spaces. Yeah? So we kind of restrict ourselves to the properties, every property that holds with high probability. Yeah? You can imagine. Yeah? In other words, we say when are two graphs G and M and SG and M contiguous? Yeah? They are not indistinguishable. They are indistinguishable under the point of view with the high probability property. You can also think of them as an enumerative question, the fraction of the things. Anyway, this is the kind of a question that we would like to answer. To answer that, of course, we have to know more about the genus of G and M. Thanks to the classical result of Ederscher and Rennie, we know that G and M is not planar when the average degree is strictly larger than 1. But we have to do more, right? This is just one direction, so we have to study more. I first focus on the more difficult part, namely the weakly supercritical regime that we looked earlier. Yeah? So when M is n over 2 plus S, and S is between much larger than n to the 2/3 and much smaller than n, because the proof is nice. It's beautiful proof. That's why. And also throughout the talk, I think this is my single proof. So in this regime, the so-called weakly supercritical regime, Doden, Krivelovich, and myself could show that with high probability, genus is asymptotically constant a over 3 times s to the 3rd over n squared. It's a very curious quantity. How we get such a result? We just let a GB denote the random graph G and M in this weakly supercritical regime. And we observe trivially that the genus of G is equal to the genus of the largest component of G. Why this is possible? Because we say indeed one can also show that the fragment of a weakly supercritical random graph is also planar with high probability. Because of the symmetry rule, once again, either the fragment consists either of 3 components or unicyclic components. Therefore, it is with high probability planar. Therefore, the first equality. Everything is with high probability. Furthermore, we can use the so-called core, the 2 core, two-core of a graph is a maximal subgraph with a minimum degree at least 2. If you think about it, equivalently, the two-core of a graph can be obtained by deleting leaves one after another recursively. Given a two-core, then by planting back rooted trees, you will obtain the largest component, of the same order. Tree, deleting leaves one after another doesn't change the genus. Therefore, the genus of the largest component of a graph is equal to the genus of the two-core of the largest component. If you have a question, you have to ask. And this is this line. And then finally, we apply the Euler's formula to the two-core C of the largest component. This is a very well-known Euler's formula because it is connected. So we have 2, Otherwise, you have a number of components here, plus 1. But because in our case, two-core of the largest component, meaning that we have one component, therefore we have this classical Euler's formula for connected graphs. So now if you look at it, what we have to figure it out, the relative orders of all these 3 quantities. And the key step, indeed a very difficult step to show, is indeed that number of faces. There are number of faces of a graph is indeed the number of faces when the graph is embedded on a minimal surface. Is f of c, so number of faces in the two-core is much, much smaller than the number of edges in the core minus the number of vertices in the core. And number of edges in the core minus number of vertices in the core is known as the axis, something surplus, axis of the core. The way we define the two-core tells us that axis of the two-core is equal to the axis of the largest component. Deleting leaves one after another, you delete one vertex and one edge, so you don't change the axis. And this is how we get, and it is very well-known result that the axis of L1 is indeed twice the quantity, because we had this 1/2, twice the quantity, and we have it. This is, as I said, this kind of thing is just an observation, and the difficult mathematical part is to prove this one. It's quite delicate. Now, once we have it, we can indeed discuss about the contiguity. How? So I just copied and pasted it. So the same setting, and I just increased this one line, this famous typical genus. So let T is that typical genus of GNM. And what we can show is that if genus is slightly larger than that quantity T, then GNM and SGNM are contiguous. I will just repeat what do we mean by contiguous. For every property P with high probability G, GNM, satisfies the property P if and only if with high probability SGNM satisfies the property P. So with the high probability point of view, they are not indistinguishable. On the other hand, if G is slightly smaller than P, this quantity, then GNM and SGNM are not contiguous. Therefore, we call this quantity T the contiguity threshold. Now, what is the implication of that is the following. In terms of the largest component in the random graph on a surface of genus G, or the graphs with the genus and most G, we have immediate consequence. Namely, when the genus is larger, slightly larger than threshold, contiguity threshold, then we know that GNM and SGNM are contiguous. Therefore, the giant component behaves like in the Erdős-Rényi random graph. In particular, the order L1 is with high probability 4 times S. This is just consequence of the contiguity. Hard work is in the second part. When the genus is much, much smaller than the contiguity threshold, we have to work harder using the so-called combinatorial version of Laplace method, or the large deviation, like sort of the, anyway, set point method in combinatorics. We can show that the size of the giant component in the random graph on surface is indeed 2 times S. Indeed, 2 times S we have seen, right? This is analogous to the order of the giant component in the planar graph. As far as the genus is much smaller than the contiguity threshold, then indeed the SGNM behaves like a planar graph in terms of the largest component. So many quantities also indeed. Right, this is about the weakly supercritical regime, and this is not all. We also have to discuss the supercritical regime when the average degrees is strictly larger than 1. Again, with the Douden and Krivelovich, we could show that indeed the genus in the supercritical regime is linear in n. Of course, I have written down d times n over 2 on purpose. Indeed, linear in m as well, because m and n are both linear in n. Yeah, so you can think of it as genus is linear in the number of edges. Likewise, genus is linear in n. Yeah, because the average degree is strictly larger than n, and this mu of d it has a very nice formula. Indeed, it comes from the number of components and so on. And this has a very nice formula coming from the number of trees and unicyclic components and so on. Yeah? So mu of d is explicitly determined. But in this talk, it's irrelevant. What is relevant is that genus is linear in n when the average degree is larger than 1. What is the consequence of it is the following. When the genus is much larger than n, then of course GNM and SGNM are contiguous. And therefore, the order of the giant component in SGNM, so on a graph, on a surface, will behave like a Schrader random graph, and where rho is this equation, the solution of the transcendental equation coming from the Galton-Watson branching process. This part is a corollary. You don't do anything. Now comes the hard work part. On the other hand, when the genus is much smaller than n, then we know that the GNM and SGNM, GNM, so random graph on the surface of given genus are not contiguous. Nevertheless, through thorough computation, it's indeed very hot indeed computation and also insights, because different things play at different orders and so on. It's really hard work. We could also show that indeed the order of the giant component behaves like in the order of the giant component in planar graph. Namely, it does have 2 critical periods when average degree is at 1 and 2, and in between we have this nice linear curve, nice slope t minus 1. This is the picture that I want to show you. Let me check whether I have said almost everything. And now, do you have any questions so far? So as I said, it's a little bit condensed. I think it's a good time to ask questions if you have any question, because then I will move into a new part.
I have a question about the convex joining or convex embedding. Tata shows that for a 3 connected planar graph, it has a convex joining, that is every face boundary is a convex polygon. So
yes,
how about
also Steinitz also shows such a thing, but here such an embedding or drawing is irrelevant. We are talking about component to structure as purely combinatorial point of view, as a connected component, whether they are connected by a simple path or not, but the way they are connected, either convex or the order of the edges around one vertex, we don't care. If you talk about the embedding, then you are talking about the rotational system, or for each vertex, how the edges are ordered. But in our case, we don't care. We just care, they can be embedded. Yeah, so special drawings or embeddings, unfortunately, we don't discuss in this part. But of course, if you define a new model, because it has to do the probability space, what kind of probability space we are talking about. Yeah, if you set up random probability space where you do consider embeddings or convex embedding, then it might give you different result, because there is a distortion in the probability measures. Yeah, so we do care about only embeddable graphs with uniform measure. They all look the same. I just put everything in one box. I take one and I see how do you look like in terms of your component. The size is like that. I don't care about how many cycles are there. I do care about the order only. How many vertices do you have? Yeah.
All right, thank you.
Yeah, welcome. Yeah, thank you very much. Otherwise, it will be too much monologue, it will be rather boring. Hopefully, I have enough time. So, if you don't have a question, then I will move into the last part of this talk. This concerns the longest and shortest cycles in random graphs. Indeed, this subject is also one of the subjects that has been studied by Adarsh Rani or discussed by Adarsh Rani, and among others, also by Aitai Komlosh and Semeredi later. So, of course, because I'm tuned for topological aspects, namely the planar graphs and so on, but I need to discuss some benchmarking result. What do we know about the classical random graph? So let me go through it. To set the scene, because I think in this conference, we do have a mixed community. So for those who work on graph theory, this will be trivial, but for those who are working in the other area, maybe it's good time to wrap up. So what is it? Given a graph G, small c of G will denote the circumference, like in the screen. What is it? This is the length of the longest cycle. Hopefully I have chosen the right one. G of G denote, it's not a genus, but girth. What is the girth? It's the length of the shortest cycle. Here, this triangle. There are, of course, this is also, so I don't talk about the unique one, but if there are many, then I do care about just the length of the shortest cycle. Yeah, so girth and circumference. L1, as before, denote the largest component. R will denote the graph outside the giant component, named the graph after deleting the giant component. I called it as a fragment. This name is coined by the Colin McDermott, who indeed defined the or he introduced the study on random graphs on surfaces. I follow the master's the terminology. So R, but nevertheless, we don't call F, but fragment, but R, the rest. Yeah, the R. If there are many more components, we can also think about the circumference and girth of the fragment, circumference and girth of the largest component as well, right? This is why. What is well known is that the cycle structure also undergoes a significant change when the average degree is around 1. If you just apply the first moment, how many cycles are there with a given average degree? It's easy exercise, and you will see that average degree d equals 1 is sort of critical point. Yeah, even from the first moment point of view. And what is well known is the following. The first result is nearly a consequence of the well-known result by Adoshwani, namely, when the average degree is smaller than 1, I'm reading this green, gray part, with a high probability, we have already seen that the graph G is indeed G and D times n over 2, yeah, when the average degree is D. G, the Adesh-Rani random graph, consists of trees and unicyclic components. Furthermore, what is well known is that the largest component is a tree. It's not a unicyclic component, but the largest one is a tree of order, indeed, log n. Yeah, having said that, of course, a tree, the circumference is 0. Girth is also 0, right? A tree doesn't have any cycle. On the other hand, we know that the G contains unicyclic component. How long they can be, indeed, they are of constant order. Yeah, so not very difficult computation. On the other hand, a harder work is done by Aitai Komlosh and Semeredi already in early 80s, that when the average degree is larger than 1, with high probability, the largest component contains a cycle. So, the longest cycle contained in the largest component is of linear order. Yeah? The largest component contains a cycle of linear order. On the other hand, due to the symmetry rule that we discussed earlier, symmetry rule, yeah, the fragment, its circumference is of constant order as well as the gas. Gas of the gas of the largest component is of order, of constant order. And this is a very well-known result by Dicom-Losch similarity. And usually, when you study the random graphs, more difficult and delicate the regime to study is the so-called critical ranges. Critical ranges when d tends to 1. Yeah, I mentioned already d. Average degree tends to 1. The right parameterization for that to capture was, as before, n over 2 plus s. Yeah. Now, the circumference and girth, or their order, changes depending on the relative order of s. So the relative of or the s comparison to the n to the 2/3. Yeah, I'm mumbling. Yeah, so in the Edersheim random graph, in the critical ranges, when the number of edges is n over 2 plus now s, and it usually behaves differently when s times n to the minus 2/3 tends to negative infinity. We call it weakly subcritical regime. Or in the critical phase, when the s times n to the minus 2/3 tends to a constant, negative, 0, positive doesn't matter. Yeah, it's constant. Or weakly supercritical regime when s times n to the minus 2/3 tends to a positive infinity. Yeah? Weakly supercritical regime. The most delicate and difficult part is often weakly supercritical regime. And indeed, strange dynamics, interesting unknown dynamics indeed occurs in the so-called critical regime. Critical random graph is rather difficult object to study. Nevertheless, what I just focus on the middle regime first. What one can show is that in the critical period, when the s times n to the minus 2/3 tends to constant, then the size of the largest component is indeed of order n to the 2/3. Indeed, there are many of them. If you rescale by n to the 2/3, it follows interesting Brownian excursion and so on and so on, but it's a detail. But anyway, the size of the largest component is of order n to the 2/3, but the circumference of the largest component is n to the 1/3 if the giant component contains a cycle. Yeah, the star. The star is subject to the giant component contains a cycle. Does it mean that giant component might not contain a cycle? Yes. And the girth, the length of the shortest cycle in the largest component is also of order n to the 1/3 subject to giant component contains a cycle. If you look at the fragment outside, then circumference is also of the same order n to the 1/3 of the same. Indeed, this picture is drawn by Misetan, a PhD student of mine. So thanks to him. I don't know whether he's listening to this talk or not. Anyway, if he's there, thank you very much for this nice, to illustrate what are the orders. Yeah, the circumference of the largest component by green triangles, the girth of the largest component by red squares, and circumference of the fragment by red disk. You can see, yeah, it's the same order here, larger, smaller. Now, this is a well-known result, and when I studied the random planar graphs, it kind of was striking that it does have different behavior. Everything becomes scaled down, it becomes smaller, outside complicated, and it inspired me. What can we say about the cycle structure of a planar graph, let's say? And the other parts, we just copy and paste of the Edersheim random graph result, thanks to the some other known result. And the most important part is here, so the third column. In the weakly supercritical regime, we could show that the circumference of the largest component is at least much larger than n to the 1/3, but smaller than some constant times n to the s times n to the minus 1/3. So if you look at it, there is a gap in the result. So it's indicated here. There is a gap, lower and upper bound, we know, but we don't know yet the right answer. On the other hand, the girth of the largest component is red, right? It's much, much smaller than the circumference of the fragment. Just to give you a kind of flavor, what are we talking about comparison to the Rashirani? At Rashirani, we had the same order, n to the n times n over s, n over s. On the other hand, in the planar graph, as I said, the planarity constraint does do something outside the giant component. One of the things is that its longest cycle is much longer because of the much larger second largest component. And what we believe is true is that indeed the correct order of the circumference of the largest component should be s times n to the minus 1/3. Why we conjecture such a thing is it's the same order as the two core. The order of the two core and circumference is pretty much related with the order of the two core. More precisely, it's related to the order of the kernel. Indeed, the kernel is those who are obtained from the two core by replacing every path by an edge. So let me wrap up my talk. So today we have seen some results on the largest component in a random graph on a surface of genus G. The most interesting picture we saw is when the average degree is larger than 1. On one hand, when the genus is sublinear, then it behaves like the order of the giant component or the largest component behaves like in the planar graph, in the linear fashion. On the other hand, when genus is much, much larger than n, then it behaves like a Rashirani random graph following the survival probability of the Galton-Watson branching process. A very challenging open question, indeed. I spent a lot of time, but anyway, a very, very challenging open question is to determine the behavior of the largest component when genus is linear in n. Anything about when genus is linear in n, it will be very interesting. The very first step toward that we did is indeed cubic graphs on a surface. When the genus is linear in n, it's already a very heavy result. Second thing that I mentioned about this conjecture about the circumference of the largest component in planar graph, we had this lower and upper bound, and we say that the correct answer should be of order n times n to the minus 1/3. We believe that this should be true, and what we also believe is that there is a cycle of linear order in a random cubic planar graph. Cubic meaning that every vertex has exactly 3 neighbors. Why such a wild conjecture is posed is the way we prove the things heavily depends on the cubic graphs as a base case. Yeah? If you are strong in such a cycle thing, it will be very nice. This is indeed even with a randomness, showing the linear size of a cycle is not very easy indeed. Yeah. Thank you very much for your attention.
Thank you very much. So let us thank the speaker. There were some questions during the talk, but I have some small remark that probably you can find also a K5 minor during.
Oh yeah. In later stage, yes, of course.
Not only K3.
Yeah.
I'm just wondering, are those thresholds sharp or not sharp?
Which one?
Several, for example, planarity or largest component on.
I think we have the right scaling, but what is not clear is this open question number 1. You know, I cannot even formulate the right conjecture about the behavior, you know, like threshold. Of course, there will be 1, but this 1 is becoming like thick and it becomes smooth, right? This 2 is appearing, this threshold, and in this regime it will happen, but in what sense I cannot say at all. I mean, I don't know what should be the right scaling so that I see the transition between these two. So this is really delicate and it should be very interesting. And also it's related to the so-called Benjamin-Shoreham local reconvergence type of result when you talk about the local structure. Here in this regime, if you look at here a component, a component, then of course the locally it looks like a Galton-Mason tree with the Poisson D. But here, if I select here locally, if I look at any constant depths, local structure, how does it look? I don't know. It's a very interesting open question indeed. This kind of a type of thing.
Did you say what happens with non-orientable surfaces?
Oh, this is a canonical question to ask. I need one more PhD student. Indeed, Mosama is one of the persons who really contributed a lot. Yeah. After finishing his PhD, he was cooked up, Mosama. He was too tough, perhaps. All these questions was orientable surface. Indeed, reflecting the cross cap, number of cross cap, it's a very natural question. And technically, it shouldn't be too difficult, indeed. It should be doable. But as I said, you should check all the details. And I need one more PhD student. And I was planning to ask this question to Mr. Tan. So I was saying somebody, right, Mr. Tan, but he was kind of drifting away from that, and I cook up some new problem. I think the cycle structure was indeed very nice. It's also, I believe that cycle structure, not only the longest and shortest cycle, but the like small cycle distribution has to do with the local structure. I mean, the Benjamin and Schramm type of local convergence might be influenced by that as well. Yeah. Thank you very much. Non-oriental surfaces is the way to go.